And thanks again for joining us today. I've really enjoyed all the speakers. It's been really fantastic to start spreading the word and to see people gather together after a year of discussions and planning. Thank you. And I hope you've seen the amazing More Than Minutes, Jenny and Claire, what they've been producing. It's fantastic. So please have a close look after. So this is my sales pitch, basically. Some dangerous questions. So why chemically analyze copper artifacts? And if you take the plunge, why analyze thousands of copper alloy artifacts? And I want to just briefly explain what information we're seeing in these data sets and what is required to extract that information, all the collaborations and the work to put that data into context. And it comes down to why REMADE, why have we invested in what we've invested in, why are we planning what we're doing, and what do we want to hear from you and the collaborations we want to build from here. And the core of it is, I sincerely believe that the chemical analysis of copper is a brilliant way of getting at people and society and real archaeological stories. It's completely integrated, and I think it's time to do this en masse again. The question of why analyze objects is a very old one. I mentioned earlier, one of the earliest analyses we used is from 1790. There's a long tradition, obviously, of people who wouldn't put themselves in one box, who are trying to integrate across different specialists and different ideas. And Earl Cayley is an incredibly influential early practitioner of what we now do. And one of his answers to why analyze coins, particularly for him, is to see the source of materials, the existence of commerce, directions of trade routes. When this kind of idea coalesced over 150 years ago now, central to it is very much a concept of scientific analysis as a dependable fixed point where the science is not up for debate. It's all the social is stripped away and we have a signal. We have something that we can rely on that then allows further debate and interpretation. And that really has dominated things for a long time within the more and more refined ideas of the provenance hypothesis. And we've got huge data sets to play with for some periods and some places. So this is what the British and Irish early Bronze Age looks like if we just do a simple scatter plot of each dot is an analysed artifact. We have over 2,100 early Bronze Age British and Irish objects analysed from a total collection maybe of less than 10,000. Real intensive science. We have huge Iranian data sets. The Roman imperial coinage, as Philip had discussed earlier, has received great attention. The biggest success, the most focused research is done by something we call the SAM project, the Beginning of Metallurgy project in Germany in the 50s and 60s. Any visitor to the Sackler has to see these classic volumes, obviously. And Hartmann, Sangmeister, real titans of the field, pushed things on tremendously. The first time I tried to plot this, it breaks Excel. There's huge amounts of data, it just science on a huge scale that we're now seeing in DNA analysis. This is when, in the 60s, this is what material science, this is the kind of attention material science received. It was the DNA of its time. How do you cope with all that data? Well, back then, they hoped, or it appeared that the empirical evidence showed that there was regular structure within the Earth's crust, that there was a shape to the metal elements that they were analyzing for that cut through all that variation. So people like Fistelius here published things on the fundamental distributions of metals in the Earth's crust, the law of the geochemical process. And they were arguing that there's a regular shape. If you take a whole assemblage and you analyze it, it will fall into a particular shape. And then they mathematically looked for that shape in this mass of data. Again, stripping away the social, getting at some underlying geochemistry that it could be a fixed point, that we could rely on the sources having this distribution because there is a law of the universe that says that this is what geology looks like. So they produce a series of mathematical models to find matching criteria, again, all in the Bronze Age, 30,000 data points, huge amounts of effort to see these matching concepts with the geological signal. This was immediately critiqued from a range of different perspectives. So experimental metallurgy started to look at, well, if you have an object and then you actually do something with it, what happens to that chemical signal? And Hugh McCarroll at the National Museum of Scotland, Ronnie Tilecoat from Newcastle, immediately start to see differences and change as soon as you actually use metal, you actually do something with it. So they have these very elegant results where they were looking at the content of samples from a blade and its rivet, and they showed very quickly, very simply, that the solid dot there is the blade, and if you rivet something, you heat it, hammer it, it will lose some of its arsenic, it will lose some of its antimony. And these changes are in a direction, and they're just through normal use. This isn't extraordinary conditions, this is everyday use, will change the chemistry. And they argued that the rigid analytical levels, that over-reliance on a geochemical law falls away, and you need caution if you're going to use provenance model to explain this chemistry, because it may change through the lifetime of an object. And we see right up to the present day practical examples of this. So this is results from looking at the Keichelberg in Austria, where there's very early copper smelting, and the red dot is the chemical composition of the droplets, the casting waste from the mine, and the orange dots are all the objects. So this excavation on the primary metal as close to the smelt as possible sees very, very high levels of impurity, arsenic, and well, not even impurity, these are alloys, 14% arsenic and antimony, huge amounts of silver and nickel as well. And it falls well outside of the envelope of what the objects eventually show when we analyze the finished things. This is the casting waste. So that shows huge chemical change through the lifetime of this operation. So they were picking up trills of pure copper full of impurities and then puddle casting them together to get towards an ingot, and then that ingot was turned into something else. And at each stage, this chemistry is shifting and changing. So if we revisit the fundamental law, it doesn't look as good. And when people actually test the fundamental law, they start to realize, hang on, this could actually be a myth. That the creation of this underlying structure of the Earth's crust that was used to kind of imprint on archaeological data may not even be true either, because this was in like the great hope that probabilistic laws of the universe could be identified post-war, and that doesn't seem to hang true. And this team says, well, exploratory data analysis can still be of great practical use. Simple display of your data, integrating it with other sources of information and creating better stories is the way to go. So if the underlying raw data may not adhere to a geochemical law, and if you use the metal, there may be changes in it, where does that leave us? Merkel, one of the most important metallurgists in our field, did a great deal of experimental metallurgy, started to play with metal, make it, refine it, important, sensible steps. And again concludes, well, hang on, this chemistry is changing through use, through recycling and mixing, through refining. And again, worries that this is just bringing confusion to the field. Even at this stage, with this quality of work, still frustrated that we can't do these simple provenance stories. So to put it in a schematic sense, is like that even if we have the prime metal, any of these further processes and use of this metal will distort it and change it and mix it and create extra things in these data. Our core belief is that this isn't confusion, this isn't a problem, this isn't something to worry about, but this is a fantastic opportunity, because this shows us the people, this shows us the history of the metal, this shows us the sequences and what's been done to it. We shouldn't hold on too closely to this hope that we'll find these ultimate sources, when what we have instead is the opportunity to see layers and layers of people making choices and doing things, and that's why we're here, that's why we do archaeology. But what we need to do is get rid of this idea of an absolute chemistry where we can find that, if only we apply another statistical approach, we'll get a better matching criteria. That's not going to work. What we need is relative chemistry where we see change. And anyone who's done a typochronology or modeled the Bayesian, run a Bayesian model of radiocarbonates knows the extra information we need in order to see people. So the extraction, the processing, the use, the reuse, the manipulation of copper alloy imprints itself in the data set. The challenge is getting enough data of the right type to find that and to show that those processes are happening. And it needs context and process. So we need to have an archaeological eye to this chemical data, and we need to admit that the chemical data is just full of archaeological stories. So an analogy can be made with, so this is this kind of radiocarbon sequence, and as Alex said earlier, this is far more embedded in many sectors of the heritage industry. Understanding the variety, all the different inputs and complexity of the system, then that individual radiocarbon measurement has to be calibrated. And then that calibration can be modeled based on archaeology and time depth series and other phases. And we can do much more extracting out of that raw individual analysis. So this is where we're aiming for. This is going to be the REMADE team in about 10 years' time. So what we need is a huge amount of data. Under the old model, one data point is fine because you've got your matching criteria and you've got your one data point and you can say, well, it came from Ross Island or the Keikelberg or any other mine. What we need instead is a huge amount of collaboration so that we can see the shape and the character and the change in the processes and the people within these larger data sets. But thanks to the Bronze Age examples I'm about to show you and our sort of the field's wider background in later prehistory, we know where that level of data, what we're aiming for. We know where that tipping point occurs, where we can shift from somewhere which is a little unsatisfactory to seeing these more social and interesting stories. So what REMADE hopes to offer is a jump forward, a chemical framework for the first millennium AD to reach that tipping point as quickly and coherently as possible. I'm sure that many metallurgists won't agree with how we're interpreting the data, but hopefully those data can be at least be fixed and believed and of high quality, and we can speed up these collaborations and these conversations. And copper is just the perfect material framework to do this as well, because it shows up in so many facets of life, across so many different places, so many different strata of society, in so many different forms, and it ties times and places and people together, and it allows us to record change in all these different processes. It is a wonderful material. So this is what one project achieved in the 1960s, looking at the early Bronze Age, where the darkest red dots are about 500 analyses. So this is the SAM project. It's a remarkable achievement and really spurred an entire field of research for the Bronze Age. And we, in the UK, we've certainly not had much like this for later periods, apart from obviously Justine's work, David Dungworth's work. We now hope to speed and build on that. Within that data, there's been lots of interesting stories that show that this model that's been seen in the lab of change and use, that does really filter through into archaeological realities. So what this map summarizes is the focus in southern Iberia of arsenic-rich coppers in the early Bronze Age, and then a quite plausible fall away of the volume of that use as you move up around the Bay of Biscay and through the channel into Central Europe. Linking those concentrations of how much of this stuff we find is a chemical change as well. So this is a box and whisker plot for arsenic. So higher up the graph, more arsenic in the assemblage. And basically in northern Iberia, where there's also a lot in the ground, there's very high levels of arsenic in that material as well. By the time we get to Denmark, where this material is rarer, by then the arsenic is much, much, much lower. And there's also seems to be stepwise changes in the intermediate places of Western France and Southern Britain. So the argument here is that we have a great deal of this material close to the source, full of arsenic in southern Iberia, in one particular shape, particular axe series, palmella points, or different local finds, which then are moving through a series of short local exchanges and being remelted into different locally appropriate types. So is this recycling or is this fresh production? It starts to get blurred, and it's very interesting how, so the metal supply for many places will be their neighbors' objects, and then they keep some, they venerate some, they remelt some. That remelting process then drops the arsenic slightly, and then we move down towards Denmark. The early Bronze Age is still an exception for this type of work because of the massive amounts of data which are initially built in the belief of chemical provenance. What these stepwise approach, there's still provenance buried within here, but what we see instead is an accumulation of metal, remelting, repurposing, reimagining, and lots of choices about what they're doing with it. And REMADE hopes to unlock the insanely huge potential of the Roman and medieval series. So another quick Bronze Age example. So this is a reconstruction of Ewart Park sword by Neil Burridge. It's very surprising to us, looking at some of the rich data sets we're remodeling, how rarely alloys were finally designed in the late Bronze Age, for example. This is the Spanish data produced by Ignacio Montero, and we can see quite distinct distributions here of tin in the bronze for axes, for swords, and for buttons, each with a different color there, with the swords actually having the lowest amount of tin, perhaps to make sure that they don't shatter, that they're actually much more robust for that shock use. When we move into Britain, the socketed axe metal and the sword metal is identical. It's exactly the same leaded bronze. So there's a great deal of debate and discussion about how iconic these swords are for late Bronze Age European life, and how specialized their production must have been, and how venerated and named, and how important they would be, and how disposable it seems the socketed axes are. But when we really get down into the metallurgy, they're identical material, even if they then had a very different use, life, and deposition and veneration. And these are the kind of concepts that we need to compare with the Roman Empire, with the medieval world, in order to see these deep connections, which is fundamentally the same material, but used in such a variety of interesting ways. So we can start to build up the journey of this metal through a series of minor trace and major element details that I won't bore you with, but we can see the bringing together of various alpine metals in France being mixed and recast, the addition of definitely English lead, mixed and recast, and then we get to the analysis and interpretation stage. And through context, through archaeological dating, through all the discussions we've been having today, we can build up a contextual archaeological approach to these data that shows these processes. And this will absolutely, and our case studies are already starting to show, this will absolutely work for the Roman and medieval world, by which time things are even more complicated and even more interesting. And so I think REMADE is trying to address a real urgent need because of the general usefulness of copper alloys, but also the potential of the resource. How does it work with connections and trade networks? How does it work politically in reorganizations of the landscape? And obviously still the raw resources that the country is so famous for. We're obviously going to look at coins, militaria. This is very nice, but also looking at cooking material and domestic metallurgy, changing people moving into the country, moving out of the country, changes of religious practice. Because this is such a rare opportunity, such a wonderful window, we're going to do everything. This is a nice project where we have to be selective, but we don't have to be too selective. And the everyday is crucial to us. To repeat myself, the fact that copper shows up in all these different contexts, it just gives us this wonderful window where we can have a unifying chemical approach which ties together so many different times and places. And obviously copper alloy objects are just an everyday tool for dating other archaeological sites and being part of all these social descriptions. And chemistry should be part of that conversation, an active participant in a conversation rather than trying to publish just individual results out of context. All of this only really comes to the fore when we look at it properly as part of ongoing conversations. So we're trying to offer a transformative amount of data, 10,000 analyses, over 100 case studies over the next 6 or 7 years, to try and cross all these regional and period divisions, to then hopefully, even if people hate how we interpret the data, there'll be endless reuses for it, and hopefully it will help spur further work. And we're very, very keen to support people in PhD studies and fellowships and extra collaborations. And the other thing to say is if we build up this framework, then the smaller, more targeted work has something much richer to compare themselves to. So I understand very much the challenge of having just 5 data points and trying to work out what it means. But those 5 data points suddenly become either mainstream or outliers or have some shape to them when you have a few hundred things to compare it to. So hopefully this will really spur master's level research and smaller case studies. I mean, Helen's already described this data much better than me, but it still overwhelms me just how much metal there is in the ground. It's absolutely, and this is obviously out of date, and you can double all these figures at least. But the portable antiquity scheme really just hammers home to me that just the size of the potential, the resource that we have available. A third of 1.6 million objects in total is Roman copper alloy, which is absolutely stunning. So this is a case study that we've already completed thanks to Richard Hobbs at the British Museum, where we sampled this incredible material, but very, very lucky to be able to sample this, obviously. High-level figurines, militaria, and some gorgeous brass. This is a picture of our new facility. So in science terms, what we've mostly invested in is something called an MPAES, which is similar to an ICP-OES, if you've heard of that. But what it really does is take a pinch of metal, about 10 milligrams, and produces a very high quality chemical analysis. The interesting thing about this particular case study was how much of the chemistry from these elite objects is unique in time and unique across the world, really, when we've looked at chemical analysis of anything anywhere. About 25% of these shows a pattern that we just simply don't see any other time. It's very, very strong in the Roman period. This is one of the things we analysed, which has this antimony signal, and it's described in the British Museum catalogue as a North African rider. And the closest chemical parallels here show up basically all over the empire, but only for a brief burst of activity. It's incredible. It shows up in Judean coinage. I won't go into the boring details, but that third column is how much of this particular very Roman material shows up. So in the very fine sequence that coinage gives us, there's this burst of activity connecting all these different fine spots around the empire with this very strange, very unique chemical pattern. The interesting thing is that this has already been seen before by Justine, by Nigel Blades, but in other contexts. It shows up very much in the Roman period, as you can see on the left, but then there's a very long tail that reaches into the Anglo-Saxon. My personal belief is that this is a deliberately processed creation, that they wanted to make this chemical composition. And then this slow decrease over time is caused by the recycling of that material and the reuse of it, because it's as originally produced of such high quality, very high quality brass, that there was a reason to constantly reclaim it and mix it and use it again. And through McHale and Talcote's work all those years ago, we can understand why this stuff is slowly oxidizing away. So it ties together huge range of places across the whole empire. It shows what an early global world really looked like compared to what a Bronze Age world used to look like. And then we see these long tails of something interesting going on. So in building up these characters and this context in comparison is vital. And we're trying to bring in tiers of analysis. So we have this wonderful resource. We're very lucky to have this legacy data. Even if the data is from Bronze Age material, those mining regions were constantly revisited. So the Great Orme that's been mentioned today has a lot of radiocarbon dates from 1500 BC, but then a huge number from 200 AD. We're using a PXRF to get large amounts of surface data very quickly and also triage our decisions about what to sample next. And we have this dedicated new lab facility in Reading. And we're very, as I'm trying to say, we're so lucky to have this community of analysts. So not only does chemistry allow us to bring together these time periods, see these deep geographical connections, it forces specialists together. It brings a community of analysts together who will often disagree about what the data means, but hopefully we can pool these resources and pool these results and build up this more nuanced picture of the past. And these are some numbers of kind of data sets that I use very regularly. So I'm sure there's at least 150,000 sort of high quality chemical analyses that are of some relevance. And these are very complicated data sets produced by a wide range of specialists. So we also need an approach to this data that accepts that all these were made by different techniques over the years. I'm sure that this can be added to still. We're extremely lucky to have all the wonderful partners you've seen present today, and more in the audience and more online. And in order to get at this huge resource, we obviously need expertise in every part of the country and in a range of different techniques and different curated assemblages. So we've invested hopefully a huge amount of time to try to bring such wonderful people together, and hopefully we can help promote those conversations and see extra things in the numbers we're producing. And we're very lucky that we've got this substantial funding so we can invest in people. So I hope you've met most of our team today. So Joe Beale has organised the conference and is our administrator. Philippa doing fantastic work with the small fines. Keith Neckenbyer, who's sitting at the back there, has joined us as our senior technician, which is a relief to run our lab. And we're constantly looking to add more expertise and wider sets of skills. We have a series of PhD students in the room, Rose Kabinski, Tasha Fulbrook, and Katie Manby, and we're looking to build a wider range of PhD network. And we have money ring-fenced for various outreach events, internships, lab exchanges, and so on. So even though we're a year in, we're still finding our feet, to be honest, but we're looking to really cement these collaborations and build on what we've achieved so far. So just to kind of summarize, there's a great deal of fluidity and change in all these data sets and all this material culture and the concepts that they represent. I'm not claiming that the Roman Empire worked in the same way as the early Bronze Age, but the same concepts and the same chemical approaches can highlight those differences and ground those changes and give us the opportunity to see new things. So obviously the object is, I mean, we've seen today how powerful objects can change individual museums or collections. We can also therefore see beyond those objects and see these longer cycles of recycling and change, and hopefully bring all that together. Despite all that fluidity, some things are still very much fixed. We're trying to produce the highest quality data we can and deposit it in the safest places so that it can be used and shared indefinitely. But on the right-hand side of that graph, we want this data to be used and reused and have a wider community of interpretation, which certainly isn't just a metal chemist. We want to go much wider than that. And there's other things that hopefully we can start to discuss about how the science of these things can feed into more conceptual ideas about, I don't like objectscapes, but it'd be interesting to discuss that. What happens to objectscapes when we can see beyond the object and see how the internal history of some of these units of material? What does a global world look like at all these different stages? You know, there is obviously great movement of people in the past and great connections, but what happens when the chemistry shows that these are actually lots of local movements and more intimate, nuanced connections rather than one great chunk? We can hopefully help a bit with the brief history of recycling, which according to this website started in 1680 AD. So hopefully we can put a few thousand years extra on that website. And there's a lot of interest nowadays in what recycling really means, because obviously we need people to recycle. And it's a great deal of the mutability of these metals in the past isn't caused by a crisis, it's caused by choice about what they wanted to have, what they wanted to show, bringing things together to commemorate and repurpose and reimagine. So I said the top sentence to a room full of DNA specialists and isotope specialists, and they were nice enough not to laugh too much. But I honestly think that the analysis of Roman copper and medieval copper alloy is a huge opportunity in archaeological science. I think it had its day. It was extremely fashionable in the 30s to the 50s and 60s. But I think we should be doing this en masse, and it'd be great if we could help in ways of creating the connections to make this a more everyday approach again. And the results we're getting are surprising, and they're delivering new insights, I hope, into real people, as well as the economy and the geography and the technology. And the idea of having these complex characters that show up at different scales of the analysis, I found that to be a far more useful concept than the idea of provenance. Provenance is still in there, but it's part of a nested series of boxes that allow us to have these more complex conversations. And it brings us together on the past, but it also brings us together as archaeologists and different specialists and allows us better conversations with the public. Thank you very much for your attention. Please, if any of this is of interest, I know we've got so many partners in the room already, but please contact us at these addresses and see what we're doing on the website. As we slowly build and build and build, we do want as many collaborations and ideas as possible. But thank you very much for coming today. Thank you.
You did an excellent job contextualising our project and also sort of summarising our aims and the potential and the challenges that we face going forwards. Does anybody have any questions for Pete?
Your case studies are under a bit more case studies. Are they mostly sites you have in mind, or sort of not for DS in mind, or is it still fluid and flexible?
We're still developing. The concept there is there's a certain amount of data that I think then becomes really useful. So the idea there was just to say, well, if we're going to focus on a particular period or a particular place or a particular style of metallurgy, let's at least have 100 examples of that, or have that connection in order to go to that next level. It was also a way of persuading the funders that we weren't completely insane and that we were seeing it in a more granular way. So we're starting to build a long list of what we're going to focus on. But yeah.
So there are object types, chronologies of objects, sites, regions. You know, it's a full range of case studies, from things like Roman figurines to a particular type of coinage, to hits in Scotland. You know, so covering all sorts of things over the full first millennium. Yeah.
You mentioned tile coats experiments with arsenical copper. Is anybody actually trying forging, remelting some multi-component alloy to see how the percentages do change at working?
Yeah, that's happened several times, and Bradford ran a superb series of experiments on tin bronze. Oxford has had a series of thermodynamic models, but based around competing oxidative loss. So, and the oxygen refining industry sort of foundry records all help us sort of constrain the variation of what really happens when this stuff is used. So I mentioned that particular experiment because it's so elegant and it came so early on in this glut of data, but that's now been followed up in great detail of these different systems.